I hope I am audible and you can see my screen. I am sharing my screen. Let's wait for a couple of minutes. We will start after 6. Okay, I think we can start. People can join anytime. Uh, Welcome to the live session for the course Sensor Technologies, Physics, Fabrication and Circuits. This is week 7. So let me introduce myself first. I am Ananya, a PhD scholar in the Department of Electrical Engineering, IIT Kanpur. My specialization is microelectronics and VLSI. I will be your TA for this session. So, as always, will start the session with a brief summary of the topics those were covered in this week. If you have any doubt or any question, you can write in the chat box or you can unmute yourself and ask. I will be in the presentation mode most of the time, so may not be able to see your messages immediately, but I will get back to you. And if there is any question that I cannot answer, then I will note it down and probably will have a doubt clearing session before the exam where I will answer those questions. So let's begin the session. So these are the few topics those were covered in this week. First topic is photolithography. I have discussed about photolithography in my last session also. So basically these are the steps involved in a photolithography process. So you will have a substrate or there will be some deposition on top of it. Okay, this is bare substrate, say, and this is substrate, and say this is some material 1, and or you can have a substrate and on top of it another material which is patterned. Already a lithography step was done on this material 2, say. So you can have a bare substrate or substrate with a deposition, or a substrate with a deposition followed by a lithography step. These three kinds of substrates and substrate plus material combination you can use for a photolithography. So basically the first step is spin coating on the photoresist. You will coat this substrate with evenly on top of it, evenly with a photoresist. Now the thickness of the photoresist, that will depend on the spin coating speed, the speed at which you will coat the resist. So for example, I was doing lithography today, so in that process I was using 6000 rpm speed for 60 seconds for the photoresist that I am using. That timing and speed will be different for different photoresist, and it was giving me a 4 micrometer thick photoresist on top of my substrate. Now few of my substrates were like this one, bare silicon substrate, and few were like this third option that I am showing you. So this is 1, 2 and 3. So few were patterned. Okay, and this pattern, the sizes of this pattern, those were not very thick, so I was and I'm hoping that I was able to get a even coat of photoresist on top of this kind of pattern substrate. So this is the first step in a photolithography process. Next is the pre-exposure bake. So the photoresist is it's a liquid, it's a chemical. So after coating it, the solvent part we have to evaporate it by post-exposure bake. Now you have to decide the time and temperature for post-exposure bake, and this is generally given in the data sheet of the photoresist, but even you can start with those values, and we need to optimize it maybe a timing or temperature little bit so that we get proper baking. Okay? This is the second step. There may be intermediate steps in between. Say you want to coat the substrate with another coating, or you want to do before spin coating the photoresist, you want to do some treatment on the substrate so that the adhesion between your substrate and the photoresist is good. All those you can do, but a basic photolithography process will have these steps, so I'm not including those other steps. Now after pre-exposure bake, UV exposure is done, where you will expose the photoresist with a UV source. So UV light, we know that visible range is 400 to 700 nanometer in wavelength. UV will be less than 400. So your source will have wavelength, say something there are different UV sources. Based on the source, you will have a wavelength which is smaller than 400 nanometer. So ideally you should get you will not be able to make very small devices using a UV source, because its wavelength is say around 300 nanometer. Okay? And the next step is development. What development means, after the UV exposure, so suppose if this is your substrate You have coated it with a photoresist, and you have done exposure. Now let's say this part of your photoresist and this part of your photoresist becomes soft due to the exposure. Now this part will become soft due to the exposure if it is a positive photoresist. If it is a negative photoresist, this part, middle part, will be soft. Actually the side parts will be hard in case of negative photoresist, because in negative photoresist, due to exposure, the photoresist become hard. So let's say we have a positive photoresist, and after exposure this side two parts became soft. Then in the next step in development, this structure will be dipped into a developer solution, and that will remove the soft part of the photoresist. And what we do normally after dipping it in developer, we dip it, rinse the substrate, or rinse our wafer with DI water, and we dry using nitrogen gun. So finally we will have a structure like this. This is the remaining photoresist. Now we can do other processes after this photolithography step. We can coat everything on top of it with say metal layer. So what will be its structure after metal deposition? This was the photoresist layer, and we will deposit a thin metal layer on top of it. So this is metal. Next we can do a process called lift off, where we will remove the photoresist layer using some chemical solution that will give us a pattern of metal layer like this. So you can see these are like two metal lines, say. These two lines can be used as an electrode for this design, for this kind of, if you want to make a sensor, you can deposit the sensing material in between, and these two like metal layer can act as a electrode. Now what is the final structure you want? Based on that you have to decide whether you want a positive photoresist or negative photoresist, and accordingly you will design the mask, that is used for UV exposure. Now the second topic was E-beam lithography. E-beam lithography is very similar to photolithography, but instead of an UV source, in case of E-beam lithography, an electron beam source is used. Now why electron beam is used as a source? We know that I think you are aware of de Broglie's wavelength. For electron it is lambda is equal, wavelength is equal to h by m into v, or h by p, right? H is Planck's constant, m is mass of the electron, v is velocity, or this is momentum. Now electrons have very small wavelength compared to the wavelength of visible light sources those are available. So using electron beam as a source, we can write smaller features. Again, the example I gave last week also, if this is a pen, using this pen I cannot make a straight line which is thinner than the tip of this pen. Similarly, we use smaller wavelength sources to write smaller feature sizes. Uh, the difference between photolithography and even lithography is that photolithography is done in one go. So we expose the whole substrate in one go, whereas in e-beam lithography it is a sequential process. The exposure is sequential. If this is the substrate, then the electron beam is moved in a raster scan manner, which is like say x movement and y movement and x movement again. So this scan is called raster scan. This is how the e-beam lithography is done. So these were first two topics. Then the third topic was etching. What is etching? Etching is a process for removal of material from a substrate. Now these are the three terms, those are associated with etching. First one is etch ripped. What it means, what is the etching thickness, say, which will be in say some nanometer or in micrometer in per second, or it can be micrometer per minute, something like this. Now ideally what etch rate you want in your processes, you want something that is controllable, right? Say if you have 100 nanometer thick layer, and you want to etch it to half, say up to 50 nanometer, then if your etch rate is very high, say the etch rate is 100 micrometer per minute, then you will not be able to control the 50 nanometer thickness. So you want depending on your process, depending on your requirement, you want your etch rate to be such that you can control the etching process. Next is selectivity. Say what is selectivity? You have a substrate, you have some photoresist layer, this is your metal layer, say, or any other layer, and you want this to remove these photoresist. Now your chemicals will come like this way and it will remove the photoresist layer. Or in case of chemical etching also, you know that say we have an opening like this, you have some other material here and you have some material here, and you want to etch out this portion of your substrate or the subsequent layer that is below this first layer. Now you want to remove only this layer, in this case only this layer. So your etching process should be selective enough to remove only this layer, not the top layer. Selectivity is generally high in case of weight etching, where it involves chemical, because chemical reactions happen between particular material, whereas it is less in case of dry etching processes, because dry etching processes are mainly physical processes. The third term associated with etching is directionality. What it means, say you want to etch out this portion of this substrate, and you want this wall to be vertical. In case of non-directional etching, so you want this structure after etching of this, you might get a structure like this. This is mostly it is true for wet etching. So this first one is directional etching and this one is isotropic etching or non-directional etching. In most cases we want this, the first type, not this isotropic etching. But as I mentioned earlier, that selectivity is usually better in case of wet etching, whereas the directionality is better in case of dry etching. So there is like a trade-off for in case of dry etching and wet etching. Reactive ion etching utilizes it's like combination of wet and dry etching. So it is a dry etching technique because it does not involve any chemical or any solvent liquid, but it uses reactive ions. So basically it is both a physical process as well as a chemical process where the reactive ion will etch the portion that you want to etch out due to the certain like chemical reaction that happens. So it's a wet it's like a chemical etching, but you are also using a physical process because these reactive ions are usually accelerated at a high speed. It hits the substrate, so it's also gives directionality in that way. So this is like a combination of both of this. This is about etching. I hope these topics are clear. I will move to the next slide if there is no question. The next few topics those were covered were related to the characterization of the material. After doing the fabrication or deposition, we want to characterize our material as well as our devices. So this is mainly about characterization of the material. So first one was optical microscopy. So we are very familiar with optical microscope, where we use a visible light source to see our images, and we use certain optics so that we get a magnification compared to like if we are looking at our structure by naked eyes. We may not be able to see all the features, but using optical microscopy, using certain optics arrangement, we able to see we able to get like higher magnification. So how we usually do, like it's very like class 2 level optics that we studied. Say, so my diagram may not be very good. Suppose we have an object here. This is one lens. This is known as objective lens, and we will have another lens here, which is the eyepiece. Now a light will travel like this. Okay. So we will have an image of this object like this one. This is our object. Again, for eyepiece it will be like this. My diagram is not proper, but I hope you are getting the point. So these two rays will merge here, say, and we get an image of the object here, which is inverted So this image is inverted as well as magnified compared to the original object. So this is how a optical microscopy works. Okay. Now again, because we use visible light, so it will the resolution of optical microscopy is limited. The resolution is calculated using this formula. Na. So lambda is the wavelength of the light that we are using, and Na is the numerical aperture, which is refractive index multiplied by sine theta. Okay. I think this was discussed in the lecture series. Okay. Now next topic was electron microscopy. Again, the difference between electron microscopy and optical microscopy is the basic difference is that using optical microscopy we can see like features which are say micron range. We cannot go below a certain range because the resolution is limited by the wavelength. Whereas in case of electron microscopy, because electrons have very small wavelength, we can see smaller features even in nanometer range. So there are different types of electron microscopy. Basically, when electron like wave of electron or electron beam interacts with a sample, what happens is that, say this is your sample, and electron beam is coming from top, then various phenomena can happen. There will be some secondary electrons, and there will be some backscattered electrons, and there will be some transmitted electrons. Now using so this is your sample. Now using transmitted electrons, the imaging you will do, that is known as TEM, transmission electron microscopy. Now using backscattered electron and secondary electrons, or you can say the reflected electrons or the electrons, those are coming out from the sample. Using those electrons, the imaging is done, and that is known as SEM, secondary electron microscopy. So what are secondary electrons and what are backscattered electrons? So you know that in our sample there will be atoms. Say this is one atom, this is the nucleus, electrons here, there will be outer layers. Okay, say there are few electrons like this, okay. Now this electron beam, that I am denoting as primary electron, those will come, it will hit say this electron, and primary electron, the energy of primary electron will change due to this electron interaction. Say the primary electron will move in this direction with an energy which may be less than the energy of the initial energy. Okay, so this is the scattered primary electron. Now this electron, due to this energy transfer, this electron will be removed. Okay, this is the secondary electron. Now what is backscattered electron? We will have atom. Okay, there will be electron in the atoms, you have another atom in your sample. So you have another atom. Okay. Primary electrons will come, that is the electron beam. Due to the electron, it will not get scattered, but it will deflect. Say it will deflect in this direction. Then say it will again deflected by the electrons of this atom in this direction. Then it will be deflected back. Okay. So these are known as, so this one was the incoming primary electron, and this is the backscattered electron. Now you can do the imaging using this backscattered electron or in secondary electron in SEM. Both these electrons will have different energies, so we can differentiate backscattered electron and secondary electrons based on the energy, and based on the energy based on these electrons we can do the imaging of the sample. Now the difference between backscattered electron and secondary electrons is that backscattered electrons usually give information about the, like the deeper of your sample, because they travel more, they travel inside, whereas secondary electron gives more about the surface information. If you want to know that what is the morphology of your substrate, then you typically use secondary imaging that is done by secondary electron. So is there any question? I hope there are people in the meeting and listening to you. Okay, listening to me. So next two characterization techniques, those were discussed in this week, is AFM, atomic force microscopy, and STEM, scanning, scanning tunneling microscopy. Okay, so what happens in case of AFM? You will have a sample, and inside the AFM instrument there will be a tip, there will be a cantilever. Okay, there will be a cantilever and it will have a tip. This can be of silicon nitride or some other material, and this cantilever can bend and it can oscillate. Okay, the top part of this tip is reflective. Okay, and so this is connected like this, and a laser or a light source typically shines. Okay, so let me do this again. Yeah, it will be easier if I make it like this. So this is the cantilever. It is connected somewhere like this. Okay, and this part is reflective. There will be a light source that will be coming here, and say there is one detector here. So lights will come to this reflective surface on top of this tip, and it will be reflected back from this mirror to this photodetector. So it will detect the position of the light beam that is being reflected. Now under normal position, it should be at the middle. Okay, now you will put your sample below it like this, Your sample will be in a piezoelectric material. That means it can the material that can gets expand or contract due to the apply of when voltage is applied. Now say in your sample there is a structure kind of like this. Now when this tip will come near this, so what will happen? So this tip is here now. Your cantilever is like this. These positions are fixed. Your photodetector and the mirror. The light reflected will be like this. So my light is not in straight line, but you are getting the idea. So earlier it was at the origin. As it moved up, the cantilever moved up. This so the wavelength, the position of the light beam shifts towards this third quadrant. Okay. Now when it will move towards this side, because this tip actually scans in XY like position, as I mentioned, this is again a raster scan kind of technique where the tip moves throughout this surface like this. It will scan the whole surface. Now as it moves towards this side, the tip position will be like this. Okay, this is your cantilever, this is your mirror, and this is the detector. Now because it moved below, the tip moved below, the light will fall here at the first quadrant. Okay. Now based on this profile, as you can see, if there is a height, the light moves towards the third quadrant. If there is a descent, then the light moves towards the first quadrant, and based on that we actually get a profile like how a surface is, like what is the roughness of our substrate. If we have different structures, what is the profile of our substrate. So this is how AFM is done. Mechanism wise, STM is bit different. It is based on tunneling current. So again, if suppose this is your sample, it has some surface profile like this. Now there will be again a piezoelectric material, and there will be your conducting tip. So this is the tip, and a current will be applied, a voltage will be applied between your sample, this is your sample, and this is your STM tip, this one. Now when this tip is very close to this sample, and there is something called tunneling current, even though there is no direct connection between the sample and the tip, but due to tunneling, this is a quantum mechanical effect. Due to tunneling, there will be a current, and the circuit will be like kind of complete. So based on that current, and either based on the current or based on the movement of this piezoelectric material, we can determine the variation of the surface. So I will not go much details into the mechanism and different instrumentation part of AFM and STM, because these are huge topics. I hope the basic idea or overview is clear. If you have any question, you can ask. I will move to the questions next. Before that, is there any question? No question. If there is no question, let's go to the problems that I have prepared for this session. So this is question 1. Question is in magnetron sputtering. So this question is from like previous week, but you already have an idea. So I hope that you will be able to answer. So in magnetron sputtering, the purpose of magnetic field is to, what is the correct option? Focus the ion beam to the target, increase the ionization of sputtering gas. C is enhance the uniformity of the deposited film. D is reduce the substrate temperature during deposition. So I'm giving you some time, 1 or 2 minutes. You can tell me the answer and the reason, like why it is like this, in the chat box. So I hope that I will get answers from your side. I have also given the basic block diagram kind of diagram of a magnetron sputtering here. So you can see the target in the substrate holder and the substrate in the position of the magnets inside of the sputtering system. Do I have an answer? No answer. So I think you already know the answer. The correct answer is increase the ionization of sputtering gas. So what happens in a sputtering? So this is the sputtering chamber you can consider, and the substrate holder. So this is the substrate holder and this is say substrate. And this is the target. These are the magnetrons. Okay, alternative south and north poles. When these are like total magnets. What happens is that in case of sputtering, an argon gas is introduced typically, and a plasma is created. So this target that that is the cathode. We apply negative charge, like negative voltage, negative terminal of the voltage to the target. In case of RF or like any other like pulse DC sputtering, that will be like alternative, but In case of DC sputtering, the substrate is anode and target is cathode. Now when plasma is created, so this become argon, this argon plus, and there will be electron. Overall the plasma is neutral, so there is equal amount of electrons and there will be equal amount of positive ions. Now you know that electrons electrons will respond to this magnetic field. So because of this magnetron, the path of the electron will deflect like this. So this is the north pole and this is the south pole. The electron will move like this. Okay. So due to these magnets, the electrons will be trapped near this target, near these magnets, and in that process of deflection, it will hit our neutral argon atoms, which are coming, say, from this side. Argon is coming. This is our gas inlet, say, and this electrons will hit those neutral argon and will create argon plus 2 electron and will actually increase the number of ionized. Okay. I'm so sorry, the electricity is gone. I hope the Wi-Fi will continue, so let me just continue like this. You know what time I will get. Okay. So if I get disconnected, then please use the same link. We will start again. Okay. Argon argon atoms will become ionized. So argon, it will hit, like electrons will hit, that will give argon plus 2 minus. Okay. So it will increase the number of argon atoms, so it will overall increase the deposition rate, because these argon ions will hit the target and it will increase the number of sputtered atoms, and that will overall increase the deposition rate. Okay, so the answer is B. So you can still hear me, right? My net is working, I hope. Okay, I don't know when the electricity will come. We'll just continue till then. I hope the Wi-Fi will work. Okay. So what is the reason? It increases the ionization of the sputtering gas and it will overall increase the deposition rate. Okay. I am writing down this line. That will give ionize more sputtering gas. That will increase the overall deposition rate. I hope this is clear. Let's go to the next question. Is there any doubt? there is any doubt on sputtering or the topics that I have covered. At least you can respond. I'm like feeling like either you cannot hear me or you cannot see my screen or my Wi-Fi is not working. If not, let's go to the next question. Cannot see anything. The question is, what is the primary advantage of using low pressure CVD, LPCVD over atmospheric pressure CVD, APCVD? Okay. The options are higher deposition rates, option B is okay, the electricity is back. I hope everything is working fine. Second option is better film uniformity. Third option is lower substrate temperature. Last option is use of simple precursor. So what is the correct answer? Again, I will give you 2 minutes to write down the answer in the chat box, and this time I'm hoping that I will at least get some answers from you. Still no answer? I had discussed about LPCVD and APCVD briefly, or briefly about CVD process last week. I hope you remember, or even if you have not attended my session, I hope that you have gone through the lecture video, so it was discussed there. So what is the answer? Before giving you the correct answer, correct option, let's go through the options one by one. So first is higher deposition rates. What do you think, where the deposition rate will be high? In LPCVD or in APCVD? So deposition rate is typically high in case of APCVD because it is done at atmospheric pressure. In LPCVD we flow a very small amount of gas, okay, but that gives us better film uniformity or better film quality in case of LPCVD. Why? Because we control the gas flow, okay, we create certain level of vacuum inside the tube of the CVD, and then we introduce carrier gas as well as reactant gas slowly. So if this is your CVD chamber, which is typically a quartz tube, or it can be anything that will sustain a high temperature, because CVD is typically high temperature process. Only in case of PECVD, plasma enhanced CVD, low temperature processes are used. And here you will keep your substrate and you will introduce gas. This gas will be carrier gas as well as reactive gas. Now in case of LPCVD, you will maintain certain vacuum level and it will pass a very controlled amount of gas to this tube. Okay. Now as you introduce your gas in a controlled manner, you have better control of your film thickness, as well as you will get uniform film, because the process will be kind of gradual, okay. The gas flow will be there will be no extra molecules like extra atoms or any particle inside this tube, okay, because we will maintain a lower pressure, and you will get better film, better in terms of uniformity, better in terms of thickness control. You can control the thickness. The control of the thickness will be more compared to atmospheric pressure CVD. Okay. So the correct option is better film uniformity. Okay. Why? This is due to uniform gas distribution or controlled gas flow, which gives more uniformity. Now lower substrate temperature, this option will be correct in case of PECVD. In case for PECVD, plasma enhanced CVD, the CVD process will overall require less temperature compared to LPCVD or APCVD. Use a simple precursor. This is same for all these because we use similar gas composition in case of all these types of CVD. There is another type of CVD, MOCVD. that is different. If you want, you can read about it. They are the precursor, they need specific precursor. Okay, but we are discussing APCVD and LPCVD. Now, if the film quality is not good, then why we go for atmospheric pressure CVD? Now see, it is atmospheric pressure. In case of LPCVD, you need certain kind of pump. You say to create the vacuum inside this tube, you will need a pump. You have to connect it using like you need to create vacuum inside this tube using a pump, some kind of diffusion pump or rotary pump, something. Now, atmospheric pressure is simple in that way. It will give you probably higher deposition rate, and cost wise it will be much less compared to LPCVD. Okay, so if your film quality is not an issue, then atmospheric pressure CVD is a much lower cost option compared to LPCVD. I hope this question is clear. Go to the next question. Which of the following option is true for e-beam lithography? The options are A, light is required for the lithography. Second option is mask process is required. Feature size is large in e-beam. Last option is sequential exposure occur in e-beam. So I have just discussed about e-beam lithography. So what is the correct answer? So when you go through the options, like you will know what is the correct answer, but think about about the other options also, whether if those are not correct, why it is not correct, and what is the correct option for that statement. Okay. So I hope that even if you are not giving me the answer or write in the chat box, but at least you are listening to me and going through the questions and you already know the answer. Okay. So what is the correct option? Option is sequential exposure occur in case of E-beam. Okay. Option D. As I mentioned earlier, sequential exposure or bulk exposure. What is the difference? In case of E-beam lithography, it is the sequential exposure. That means you will have the electron beam, and this is your sample, the top surface, and you will scan from one end, go towards that side like this. Again you will take a step, again come back, will do a scan like this. This is known as raster scan. Okay. Now depending on your design, say at this portion you want exposure, you will do the exposure. You will go back, go to some other place where you want exposure, then you will do the exposure. But typically this is how the scanning is done, and this is known as sequential exposure. So this is the raster scan. What happens in case of photolithography? You will have a mask which is typically a a pattern of chromium on a glass substrate. These are not normal glass slide that we have, but it's typically a thick glass, and then there will be some portion that will be dark. So this portion is chromium, and then you will expose the sample which is below this mask. The sample will be in contact with the mask. Okay. And you will do the UV exposure as a whole, like at one go. So different portion of the sample will be exposed simultaneously. So this is not sequential exposure, this is bulk exposure. Or I don't know, there may be other term which is equivalent to bulk exposure also. Now photolithography is much faster because you expose the whole sample in one go. Okay, at least you can make like a few centimeter cross few centimeter circle, few centimeter cross few centimeter sample, or say 1 inch or 2 inch diameter wafer. You can do the exposure in one go. Now if in industry maybe that exposure will be will be a much larger area. Like in our lab also we can do like a 2 inch diameter exposure kind of size. But in case of E-beam lithography, your exposure speed or overall lithography speed will be very less, because if you do sequential exposure, So this is very time consuming. On top of that, even lithography, the instrumentation is very costly. Okay, instead like a photolithography instrument is um, the cost is much less compared to e-beam lithography system. But the advantage is that using e-beam lithography we can get feature sizes which is in the nanometer range. Okay. Let's go to the next question. Question 4. So the question is the steps in correct order for etch-back process is. So the first option is you will start with a substrate, then you will do metal deposition. After doing the metal deposition, you will spin coat the photoresist, do the photolithography and develop. Then you will get the substrate with patterns. Then you will do the etching of metal. Okay. And the last step will be removal of the photoresist, and you will have the metal deposition with the portions you want. That is option A. Option B is you will start with a substrate, will do the metal deposition and lithography. After lithography, that is the after exposure, we will do the development in a solution, develop a solution. We will get the substrate with pattern, do the metal etching, again spin coat the photoresist, and finally remove the resist. That is option B. Option C is you will start with substrate, do the metal deposition and lithography. Again do the spin coating of photoresist. So here photolithography means the UV exposure. Then you will do development. You will get substrate with pattern. I will do the metal etching and then remove the resist. The last option is option D. We'll start with substrate, do the metal deposition, etch the metal, and then you will do the photolithography process. That means spin coating, exposure and development. Okay. So what is the correct order? What is the correct option in case of etch-back process? So this photolithography means UV exposure. Photolithography is the whole process, it's not only the UV exposure. So what is the correct option? So what is etch-back process? So the process flow is like this. So when you do a lithography, you make process flow. So that so it involves multiple steps. If one goes wrong, you will not get the correct pattern, or you will not get the desired dimensions. Okay, so you make this process flow. So you will start with a substrate. Okay. This can be a bare substrate, or something deposited, or something patterned. Okay, I'm just calling it as a substrate. On top of it, you will do the etch-back process. Next step is metal deposition. This is metal, this is your substrate. Now how you will deposit metal on top of the substrate? By any physical or chemical deposition technique that we have discussed. Or there are other techniques also, those were not covered, but you can do a CVD or you can do a PVD process. Next you will do spin coating of photoresist. Okay. This is your photoresist. Now the thickness of the metal, that will depend on the thickness that you want finally, the metal thickness, and the thickness of the photoresist, that will be like the thickness will be like the process that you have already optimized, the lithography process. Okay, what we normally do is that for certain thickness of photoresist, we do exposure for certain amount of time, and we do the development for certain amount of time. So those parameters, the exposure time and development time and the thickness of the photoresist, those have to be optimized before starting the before doing it on the actual device or your actual substrate. Okay, or the final substrate. Okay. Next you will do UV exposure. There will be intermediate steps in between. You will do post baking on the photoresist because you want to remove the solvent part in the photoresist. Okay, that I am not including. So you will have a UV source, you will have a mask. Okay, so this is dark, this portion is dark. Okay, this is UV, and you will have your sample here. Okay, after that you will do development. You will dip your sample in a developer solution. Now if it is a positive photoresist, you will have photoresist at the sides and in the middle. No, you will have photoresist in this areas, dark areas, other areas it will be gone. So after development, patterned photoresist will be like this. If it is a positive resist, okay. If it is a negative resist, the pattern will be opposite. So you have substrate, you have metal, will have resist here and here, okay. Then when you will do metal etching, okay. Now you are doing etching on this metal part, not the photoresist part, okay. So after etching, you have some chemicals say that will etch with the metal part, because the photoresist is covering the metal part. So that in that portion metal will remain. You will have a structure like this. The metal will remain here and here, and you will remove the resist. Finally you will get the metal pattern like this. So this is etch back process. The process I discussed at the beginning of this session, that is lift off process. Okay. In that case we do the metal deposition last in like after the lithography. In this case we are doing the metal deposition first before the lithography. So the process is a bit different. Okay. So what is the correct option? Substrate, then metal deposition, and spin coating of the resist, UV exposure, development, that will give us substrate with pattern, and will do metal etching. So this is like a very selective etching because we are removing the metal part only, and then we remove the resist to get the final metal pattern, okay. So this is the correct option. My diagram is like really bad. I hope you don't mind and you get the idea what I want to actually explain. Let me go to the next question. Dry etching is used instead of wet etching because the options are to have isotropic etching, second option is to use in a batch process, this is S, option C is to avoid undercutting. The last option is to have high selectivity. So what is the answer? Okay, if there is no answer, let me go through it. So what are the parameters that I have discussed in case of etching? So we have few parameters. Those are selectivity, directionality, and etch rate. Okay. I have mentioned that selectivity is good in case of chemical etching, that is wet etching, because certain chemical will react with certain chemical composition of the material, and that will achieve it. Whereas the directionality is good in case of dry etching. So what it means is that that there are two terms, isotropic etching and anisotropic etching. So if your etching profile is like this, and you what you actually wanted was like this, say, okay. So you wanted this vertical wall, that means that is like a directional etching only in this direction, say it is the z direction, but you are getting etching at the xy direction also. In this case, in all the direction x, y, z, all the direction, the etching is uniform, so this is known as isotropic etching. That is why it is known as isotropic. Okay? Uniform in all direction. And this is anisotropic etching. Now here you can see that in case of isotropic etching, even though your opening was like this size, but ultimately you are getting a size of this. Okay. So this problem is known as undercutting. Certain areas of your substrate or this material, you don't want to remove it, but it is getting removed due to isotropic etching. Okay. Now this is more prominent in case of wet etching. And this kind of profile we generally get by dry etching. So this undercutting problem that is there in case of wet etching. So in for dry etching it is preferred over wet etching because it can avoid undercutting. Okay, so that is the correct option, C. Now let me give you some differences between dry etching and wet etching. So let me make a column dry etching and the side wet etching. Okay, so this is H. Okay. So dry etching involves like reactive gases or non-reactive gases. It's a physical process, whereas wet etching involves chemicals or liquids. Okay. So that is the basic difference. That is the basic definition of dry and wet etching. I will not write it here. This gives no undercut, no or less can be. And wet etching gives mainly isotropic etching. In case of dry etching, selectivity is poor unless you use reactive ion etching. In case of wet etching, selectivity is good. So this requires, this is more costly. Okay. And you need if this is done using like proper instrumentation. Okay, so have an instrument for dry etching. Okay. And in case of wet etching, if the chemicals are not very expensive, then it is relatively lower cost. Okay. Dry etching is expensive mainly due to the instrument. If it is a reactive ion etching, then it is even more expensive. Okay. There can be like certain hazards related to wet etching because those etching chemicals are generally toxic or not good for our health. So this can be certain hazards associated with wet etching, but it is a relatively simpler process compared to dry etching. Whereas in case of dry etching, it is mostly done by the machine. You control it from a control panel, and this is much more safer if proper precautions is taken. So I hope it is clear. Is there any like question on dry and wet etching or on etching in general? Okay, thanks at least. I'm getting some confirmation. So go to the next question. So match the following. I'll have one column and another column. You have to match. first column is optical microscopy. Transmission electron microscopy. Three is scanning electron microscopy. So this is STEM. This is SEM. Fourth is EDEX. On this side we have, first is X-ray detector. Second is easy sample preparation. Third is detection of shadow of object. Last is backscattered electron detection. The options are A, 1 to 2, 2 to 5. I am giving you the options, so you can give me the only the correct option, A, B or C, D. Okay. 3 is 3, 4 is 1. B, 1 is 2, 2 is 3, 3 is 4, 4 is 1. Option C is 1 is 1, 2 is 3, 3 is 4, 4 is 2. Option D is 1 is 1, 2 is 4, 3 is 3, 4 is 2. So what is the correct option? I will wait for 1 or 2 minutes that you can answer. there any answer? Okay, let me tell you the answer. So let's go through this one by one. So first is optical microscopy. So the option that matches this side is a sample preparation. So this is one. Because in case of optical microscopy, like it's very simple. You put your sample under the microscope and you see through the eyepiece, or you see it in the computer if an camera is connected through from the microscope. Okay. There is no complexity in related to any sample preparation. Whereas in case of TEM, transmission electron microscopy, the sample preparation is not very easy, because what happens in case of TEM, the electrons will travel through your sample, and based on the transmitted electrons, the imaging is done. So first of all, to get the TEM image, you should get transmitted electrons. That means your sample, do I have an answer? Answer is A. Okay, let me, I will go through these options and then we can decide. Okay. So in case of TAM, you actually need a very thin sample. There should not be any charging, so that electrons will pass through your sample and you get some transmitted electron, and based on those transmitted electrons, those energy of the transmitted electrons, you will do the imaging. Okay. But what you can get in case of TEM is the detection of shadow of offset. So if you have a sample like this, and say there are some nanoparticles like this. Okay. Now if your electron beam travels like this, you will get a shadow, like we get a shadow, like our shadow, or the shadow of a tree or a house, that is for visible light. But in case of electron also will get a shadow if this beam is like this and transmitted electron is like this, so we'll get a shadow of this particles. Okay. This is, say, nanoparticles on a substrate. You can look in Google. You can just type TEM images. You will be able to see this kind of imaging where you will see the shadow. Okay. This is for TEM. Now if the beam is like vertical, you will not see the shadows. You will see some contrast due to these particles. Okay, because it's like a black and white image or a grayscale image. So but if your beam is like tilted, you will see a shadow like we see in case of visible light. Okay. So this for TEM, the correct option is detection of shadow of object. So this is 2. Okay. Next is scanning electron microscopy. I have discussed about SEM in the beginning of this session. So in SEM, we can do the imaging either by secondary electron or by backscattered electrons. Now what are backscattered electrons and what are secondary electrons, I have already discussed. You can go back or look, I will share this slides with you. So you already know what is what are secondary electrons and what are backscattered electrons. Those are used for imaging in case of SEM. Now I have also mentioned that The secondary electrons and backscattered electrons will have different energies, and in SEM, inside the SEM instrument, we have a backscattered electron detection detector that will detect the backscattered electrons based on the energy of the electrons, and using that we can do the imaging of backscattered electron. Okay, and why we do imaging using backscattered electron, that also I have mentioned earlier, that backscattered electrons typically give deeper information. It gives more information about the composition of your material, composition of your film. So you have different types of elements, then backscattered electron can provide you some information about the placement of different elemental composition. Okay, so the third option is, this is 4. Okay. Now EDEX, I don't know whether EDEX was discussed in the lecture videos or not. Briefly I will discuss. Okay. Suppose you have some atom, this is the nucleus, there are electrons here, there will be outer shells, okay, and there will be electrons here also. I'm just representing, giving you a representation. Okay, so this is nucleus and these are the electrons. Okay, now when you do, so EDEX you can do, what is EDEX? Energy dispersive X-ray spectroscopy. Okay, EDEX means energy dispersive X-ray spectroscopy. Okay. Again, it's a large topic in itself. I'm just giving you an idea. So what happens? So this can be done. EDEX analysis can be done along with SEM. When we do SEM imaging, you can also do EDEX. Why we do EDEX? This is to get elemental composition. So suppose you have a film, and the film is of SiO2 cell. So ideally you should have the certain ratio of Si and oxygen, silicon and oxygen, so that you will get actually SiO2, not some other form. So you do EDEX to determine that. Now suppose you have some impurity in your material, say you have carbon, you have some extra ions or extra element, that also you can detect using EDEX. So how it is done? So when you do SEM, you will also how electron will interact. So the imaging is done due to the scattered electron. EDEX is done mainly from the X-ray, okay? The X-ray that is emitted. So when an electron from the electron beam come towards your material, so this is your atom, say it will remove this electron, say. So this is the core electron, see, it will remove. Okay. Now when this electron is removed, it is knocked off by your incident electron beam, then an outer cell electron will come to fill this gap. So this electrons will come here. Now the outer layer electron have more energy compared to these electrons. So when it comes here, this fills the gap, so it will release energy in form of X-ray. Okay, it releases energy in some form of X-ray. characteristics X-ray. Say this is known as K alpha, this is K beta. Now let's not worry about what is K alpha and K beta. I'm just giving you the notation. This K alpha and K beta is say energy of the emitted X-rays. Okay. Now the energy, this K alpha and K beta energy, uh, this energy will be specific for specific element. Say for carbon, this is the value of this energy of the X-ray, and say for oxygen it is a different value for the characteristics X-ray. Now based on the value you can actually determine in percentage. Generally we get the elemental composition of the material in percentage. Say you have this many percent of oxygen in your sample, this is the percentage of carbon in your sample, okay, and say this is the percentage of your silicon in your sample. Now by looking at these numbers, this value, you can say whether you are getting the correct composition or not, okay, and if there is any impurity in your material. Okay, this is about EDEX. So what it needs, EDEX needs an X-ray detector because it is detecting the energy of this characteristics X-ray. So option 4 is, so this 4 matches with this. So what is our correct answer? 1 is 2, 1 is 2, okay, 2, 1 is 2, 2 is 3, so this is our correct answer. Great. So our answer is B. So I hope it is clear. Is there any doubt in this characterization of material? I have not gone through this in detail because some of these were discussed in the lecture videos also, and these topics in itself, these are very broad topics. We are just giving you an idea how it is done. Suppose you want to make your sensor, you want certain sensing element, certain material. Say if it is a metal oxide semiconductor based sensor, MOS sensor. So what is one example of a MOS material? That is say ZNO or SNO2. So after depositing your material on a substrate, can be anything, but you should have a good adhesion between your sensing element and your substrate. After doing the deposition, what we do, we go for characterization. Optical microscopy, so we'll see that if there is some non-uniformity in our sample, if there is any scratch or something, so we just by looking at optical microscopy you will know that. And suppose in many cases our sensing element will be like nanorod structure, nanowire structure. To determine those, we go for electron microscopy, and whether you are getting the correct material or not, that the elemental composition we can do using EDEX. So this is briefly about these characterization techniques. I hope these are clear. Is there any question? So I hope the topics those were covered today, those are clear. Thank you for attending the session. We will meet in the next week or maybe in the middle for some doubt clearing session. If those sessions are organized, you will be notified prior to that. Okay, so thank you everyone. Have a nice day. So I'm ending this presentation or like this meeting.